For the past several years, we've worked in collaboration with Mazak and Autodesk. More recently, we've worked with them to accelerate the adoption of hybrid manufacturing by demonstrating the latest machine tools, the latest tooling, and the latest software for this technology. Today we're demonstrating an aerospace component. Typically in aerospace, the components are made out of high-value materials and materials that are quite difficult to process. These materials tend to come in large billets, and then we remove a lot of that material to get to the final geometry. This obviously takes a lot of time to machine, and the material is quite costly to begin with. Hybrid manufacturing offers the opportunity to reduce the waste material and also reduce the cost of machining.
The machine behind me is a Variaxis J600 5XAM. It's a full 5-axis vertical machining centre with the added capability of additive manufacturing. The block itself, which is the hub, we're using Inconel 718, and to build the blisks themselves we're using Inconel 625. So using this material can be quite challenging when you're trying to machine things. You have to run things quite slowly with small depths of cut. This costs a lot of money in machine time as well as tooling. So the great thing about this technology is building the net shape so you have a lot less material to be cutting.
Hybrid manufacturing has several challenges. One of these challenges is around managing heat input into the process. So heat input in the process leads to a lot of internal stress in a geometry. And this can lead to distortion of that geometry, or in some cases, cracking or failure of that component. So for this project, we've used two different Autodesk products. Firstly, we've used the power of Fusion 360 to create the CAD model for the geometry. In conjunction with that, we've also used Fusion 360 to create what we call the deposition model. And this is a geometry which is slightly larger than the CAD model that represents the additive deposition. Once we've finished in Fusion 360, we've then taken that geometry into PowerMill. Now in PowerMill, using the PowerMill additive capability, we're able to create the additive toolpaths to drive the metal deposition process. Then, also being in PowerMill, we're able to create the machining toolpaths to reveal the final component. Using Autodesk's NetFab simulation utility, we have the ability to simulate the additive component of the hybrid process. This allows us to see heat input, internal stress, and distortion within a component during the additive process. This information can then be used to make changes or inform decisions on how we deposit the metal.
So hybrid manufacturing is coming more and more to the fore, and it's something as a subtractive manufacturer we could have shied away from, but we've actually embraced. And seeing this technology emerge in the market has influenced the design of our tooling. On this demonstration, we have a combination of some of our solid carbide offering, and in preparation of this demonstration, also some of our advanced material tooling, essentially ceramic inserts. So we've looked at putting tools on there that offer great tool life and stability and resistant to damage caused by the rough surface, whilst also still offering productivity and stability.
So one of the great things about this demonstration is we can show the user that this machinery is commercially available. We've got great cooperation with our partners such as Autodesk and Seco. Everything is available on a commercial basis. We have enough research and knowledge now that we've developed over the past few years with our partners that we can take a customer's project and move it forward and use additive manufacturing to the best of its ability.
So you can learn more about Autodesk manufacturing solutions by visiting autodesk.com/make.